So this is a bit of a unique moment. You may not realize it, but you have two people on the stage today, here, right now, who have only first names. Philippe Antoine is someone who has been with OISF for a number of years now. He's been working on making Suricata more robust, driving our fuzzing effort. He's one of the reasons why we push out so many point releases. And has been, just in general, been working on features as well as general code improvements. So the recent work on Quick is in large part by Philippe. The work on HTTP2 is, for the most part, Philippe. So he's been working hard. And I think he got more and more curious about, all these OSS fuzz bugs and, how you might be able to abuse them to, get a bit more out of your bug and security issue. So please, warm welcome for Philippe Antoine.
Thank you, everybody. So, yeah. In order to try to make Suricata more robust, I guess I will break it to think about how to make it more robust. That's the point of the talk. Build an exploit against Suricata to improve its in-depth defense. So Victor has already said much about me. I love open source, network traffic analysis, fuzzing. I have been a Suricata developer for 3 years, and I have my own freelance society, Catena Cyber. And this is the first time I developed an exploit, so I was completely a newbie before this work. And so today we will just quickly look the vulnerability and then spend most of the time building the exploits, and as a conclusion, think about the countermeasures that we have been adding or that we could add in the future. So let's start with the vulnerability. It was found by the excellent OSS Fuzz from Google. So you have the bug ID if you want to go there, and we first got this stack trace, and my first impression was that, yeah, there is the range stuff, which was a feature that I added that already had many bugs, and I said, okay, there is one more bug to fix. But then looking deeper, it was not really the case. So we see that analyzing the stack trace and what's happening, there is this protocol change going on. So maybe to give a better illustration, here is the pickup that triggers it. So it looks nice at the beginning. We start with some SMTP, hello, start TLS. But then the server does not answer TLS. He answers HTTP 1.1, upgrade to HTTP 2. Okay, it's a nice find by fuzzing, because as a matter of fact, it triggers the protocol change while there is already a protocol change. The server is asking to change from HTTP 1 to HTTP 2 when the client is asking to change from SMTP to TLS. And this overwrites this alproto oric field, which is then being used to clean the states of the app layer protocol state of the flow. So, yeah, to sum up the analysis, we start with SMTP, start TLS. We request a protocol change, saving that the original protocol was SMTP. We recognize HTTP1. We parse HTTP1. We say, oh, now we want HTTP. We request a protocol change, so we save that it should be HTTP1 origin, but in fact it's SMTP, and so we call the HTTP stage 3 with SMTP state arguments. And so the fix was simply this. So if we are already doing a protocol change and there is another request, we do not accept it. So simple three-line fix and good big bug prevented. A bit more about the vulnerability. So it was introduced by me by adding the HTTP2 support and especially the HTTP1 to HTTP2 upgrade mechanism. Even if the patch is in another part of the code, which was making the assumption that multiple protocol changes were not happening at the same time. And OSS first found it with SMTP as a start, but there are other protocols which can request protocol change, and it's there is the same bug with FTP and PostgreSQL. For releases, the bug was present in a version from 6.0.0 to 6.05, not with the default configuration, because HTTP2 was experimental on version 6, and you have the commits range in the master branch if you want. And to give the timeline with dates, the bug was introduced in March 2020. The first target that found it was introduced last September when preparing the talk for SuriCon about fuzzing. Say, I could add this target, it should find bugs. And it took 6 months to find this bug, even if it was already present. So it has been living for 2 years. So it's fuzzing was good, but it was not super fast to find the bug. Okay, so this was the simple part. Now let's build a simple exploit. So I will get crazy with my hair to get arbitrary code execution. And to do so, I will first fail and learn, and then succeed and refine a bit. So here the scope of the vulnerability, which is a type confusion, is quite small in time. There is only one function, which is HTTP stage 3, that will use the corrupted argument. We cannot do anything else with it, but we have some, as an attacker, some freedom about what to choose. We can choose either FTP, SMTP, or PostgreSQL state and try to mock it as a HTTP state. And so this HTTP state 3 function does quite a few things. So here I highlighted the one that will be interesting. And so you see that we have the state, which is called S, and there are different fields that are used: conp, file range, files TS to server, files to client. so we can match the structure. So the SMTP stage structure with this argument, conp, file range, files tc, and FTP state or SMTP state structure. I did not add a Postgre because I did not get the Rust memory layout, and I managed to do it without PostgreSQL, but there is maybe something to be added. Yeah, and so we can have one FTP state or SMTP state structure, but we cannot have whatever we want. And as an attacker, we have to deal with constraint that this protocol state must be reached at the end of the parse function when SuriCata requested a protocol change. Because when there is a protocol change, as you see, we break out of the loop and we stop parsing everything, which is good. And so first for FTP, looking at the constraints, yeah, we have this direction field, which will be 1 because we will request the protocol change only in the response parsing side. And we will have the FTP gain light state that will set input len to 0. And so, input is not 0. It's on the original input plus input len. And so for the attacker, that was a problem because the first field was not 0, and then we had a second field which has a fixed value of 1 and 8 zeros. And so in HTTP stage 3, the first lines of code check if the first scene is 0, it's not 0, and then we do some more function which will difference the address at the second variable, which is fixed, which is 1000, and then if there is some memory there, it will difference it again and again. And so we just segfault because at some point we cannot read the memory. And so, yeah, SuriCata was successful to prevent exploitation by having these variables which or direction input len that were outliving their scope. They were only useful during one call of the parse function, but they should not have remain living in the states. So yeah, so that was on 64-bit system. Maybe on a 32-bit system there is something to do. But yeah, as an attacker, we have some degrees of freedom, but we have some constraints, and it does not work always. But yeah, this was FTP. I have SMTP. And to do this talk, I also gave myself the permission to look into the whole range of commits where there was the vulnerability. So the state structure evolved during 2 years. So the matching of structure evolved. And yeah, before yeah, at some commit for the SMTP structure, it's quite interesting because we have the first field, which is always 0 because we have the SMTP transaction complete that sets it to 0. The to-server last data stamp is 0 as well, so there is no bothering us. It's yeah, it's null. We will not try to free it or do something with it. There is the files tc. It's orange. It's not 0, but we will try to see it afterwards. And there is the especially interesting file range in HTTP, which is matched to some buffer, tcgb. And this file range is used with another big function, HTTP close handle range. And tcgb is a pointer to a buffer of completely controlled input by the attacker. The only constraint here is that this buffer cannot have a new line in its content, so the ASCII 10 character. So yeah, we have a type confusion again, but now we promoted this type confusion. Instead of having constraint, now we can have arbitrary buffer without new line. And so we can pack this structure and say to Suricata, yeah, this is a HTTP range container block, and I put whatever I want. And yeah, whatever I want, you will see it's going to be a 1, 0, where, and what. Because when we get deeper in the code, there are some stuff happening and that we will need to survive. And we find some gadgets, which is C container files equals C files. And we control the contents of C completely. So this is arbitrary write what, where. So we have the constraint of not having a new line, and we cannot write anything. We can write anything except 0. But that looks powerful enough. So at this point of studying the code, I patched Suricata to get an easy exploit. So I commented out the files tc stuff. I commented out, when I went deeper in the code, some mutex lock logic. I added a function which I called system exploit, which was running a system whatever command. Yeah, that was the patch. Okay, so I found the address. So yeah, I know what to write. I want to write the address of this function, but where should I write it? And I met the mitigation, which is ASLR, address space linear randomization, which basically at each Suricata run, if you compile with it, Suricata will live at a different place in memory. So I disabled it with my compile flags to have an easier exploit, and you should not disable it. And I looked for a global constant containing a function pointer to overwrite my function pointer with my system exploit. And I crafted a pickup with my strict.pack where what. And it was working, and I was really proud. And then someone in the team told me that this is not a real exploit because I changed the source of Suricata. So yeah, now I had succeeded, but now I need to refine. So I need to get back unpatch Suricata, all the three things. First thing is to survive the locking stuff. So if I uncomment it with my first exploit, it was crashing before getting to the exploit. So I need to survive something that differences some memory and writes into it before being able to overwrite some function pointer. And so I discovered LLDB scripting. So LLDB is the LLVM debugger, and you can have Python to do whatever you want. And so that's what I did. I just scanned the whole process memory and say, hey, is this at offset plus 16 writable, and is this at offset plus 40 some function pointer? And is there something like it? And yeah, there was one thing which I was FTP malloc. Okay, so I managed to get it. So I do not use the first function pointer, but this sbcfg.malloc to overwrite, and no crash, because there is a function pointer, but it was unused. So yeah, Suricata prevented execution another time with some useless feature. But then I found out a solution, which is to chain writes, because in the end, I need to overwrite a function pointer, but I can get to it in multiple steps. So I added a loop in my LLDB scripting, and it found another interesting occurrence of HTTP range 3 block. Okay, so this made me do ugly scripting, and so I started a bash script that called Python script that created different pickup before merging them all together. So each unit pickup overwrites something, and yeah, in the end I overwrote the function pointer and can use it. So next was to get back the files TC to not to crash. So we have a dangling pointer at the end of SMTP parse is input plus input len. And the function that will be called with it will try to difference it. And so the solution was to have the input to have the right length, so that input plus input length points to some next buffer. So the length being 2048 bytes, and then I create some dummy stream, and it has also the streaming buffer. And so yeah, when we will free something, it will indeed free something, and so I can live on. And it's not completely reliable, this step, so I hope that my demo will show you that it crashes sometimes at this point. Yeah, and so getting more and more complex with the scripting, and mixing packets so that at the right point, Suricata does the right allocation of 2048 bytes. And next was not to use my added function system exploit, but relying on what is already in So we overwrote, we are overwriting the pointer SuriCata context.http range free block, which gets one HTTP range container block argument, which can be an attacker controlled buffer. So the buffer got freed at the point, but we, depending on the libc, the buffer was allocated 112 bytes after, and yeah, the contents are still there and not and have not been reset. So to get the arbitrary code execution, I want to use the libc system function to run shell commands. And I want to find a gadget that will run a function pointer from a structure with data from the structure. And one which has big offsets. And yeah, I found one which was, in fact, one of the functions I had looked for earlier, because it's called by SMTP Stage 3, which is the destroying of decompressor in libHTTP, which use offset 367, and we see the destroy, which call, so destroy is a function pointer of comp, and it uses as argument point comp. Yeah, and function pointer is at offset 16, so we have like a 15-byte arbitrary bash command with it. So we combine all this together. We have unpatched SuriCata, and to sum up, we overwrite the HTTP file close underledge to point to HTTP con destroy compressor, and we overwrite some memory, a bit random, with 16 bytes of arbitrary bash command, and then a libc system function pointer. And we send a HTTP2 range response with the buffer having this memory M pointing to what we want. And yeah, so demo time. So this worked, it's on the left. So I have LDB, so I run with some options with my pickup. Yes, I want to start again. So as I said, I hoped that the file container would fail sometimes, so start again. And yeah, so 2 fails and 1 success. And so my arbitrary bash command is a list directory and echo Pwning somewhere. And if we want to see the backtrace, we can see that, yeah, the HTTP2 range parsing called the comp destroy decompressor, as it should not have. And then after executing some arbitrary bash command, it crashes because, yeah, I did not set everything right, but got arbitrary command execution. So, yeah, if I were a real attacker, I would have further work to bypass address space layout randomization, to have more reliability against what was failing with the dangling pointer, to survive the arbitrary code execution. So yeah, I can run arbitrary code and SuriCata keeps running. Yeah, that means restore overwritten memory, I guess, at some point. Maybe I want some bigger arbitrary code execution, more than 16 bytes or 15 for bash commands. And to do so, maybe I can find and use better gadgets. Okay, so I've got not so much time left to look for the defense countermeasures, but yeah, first I guess is to find these vulnerabilities and find them. So we have fuzzing, we have static analysis tools. If someone wants to fund a bug bounty for Suricata, be welcome for it. We have Rust, so yeah, if Suricata was 100% Rust, this vulnerability would not have happened. We will not have type confusion, but yeah, before getting to that part of the code, I guess we need to have at least 50% of Rust in Suricata, so that's a long-term goal. We should reduce attack surface, especially function pointers, which is a convenient way to bypass the protection that memory is either writable or executable. So to disrupt code flow, an attacker can use function pointers. Yeah, lots of other ideas. So reduce function number, make them read-only. So the Rust context function pointer that was used is now read-only, for instance. So that's what we can do. What you can do when you compile Suricata is get the best of your compiler, and especially ASLR, but there are more features. We can also ask the kernel to watch over us, so that's what Victor mentioned. We added the call to setter limit nproc 0, so we ask the kernel that we are not allowed to create a process. So yeah, Padme is asking why, but maybe we will turn to the dark side and yeah, just prevent us before we do so. Yeah, maybe we can have more from the kernel to prevent us from doing bad things. And then, yeah, you can also have more with system isolation, with non-lock, with not running as root, etc. And to conclude, you can do a bit of forensics with this vulnerability, because to trigger it, the attacker needs to take code paths where we generate anomalies. So you can look for this anomaly of no TLS after stat TLS, unexpected protocol, and unable to match response to request, because there is the HTTP1 server response without a request. And you can also look for flow where the protocols as FTP, SMTP, HTTP are different event types of protocols that should not happen. And this is good because it worked on the vulnerable version, but there was a bug in anomaly generation, which was issue 5391. So maybe you do not have all the anomalies, but you should at least have some of them. And you can now also add rules to detect this. So this is a couple of rules to with a flow bit to check that here we have some unexpected protocol during protocol change, and then we have some HTTP1 trying to upgrade to HTTP2. So as a conclusion, I prefer patches over exploits. I hope not to build more exploits again. And yeah, we strive to make Suricata more secure. If you have ideas about the other defense countermeasures, they are welcome. And make sure your Suricata is compiled with address space layout randomization, because I think this is hard to bypass in this case. I mean, we need another vulnerability, so it's significantly harder. And yeah, your ideas are welcome, and sorry for taking too much time. Thank you.
No questions at all? This is it, last chance? He already took up all of his time and then some. You all know how we like to stay on time here at SuriCon, right? Okay, that's it. Thank you so much, Philippe.
Thank you. You can ask me questions later if you have some questions.
Victor, you're up.